Good morning, AP Calculus. Today we're going to take a look at transformation of a specific type of function, and those are our trig functions. Before we get started, here are the solutions to the warm-up that you had to do for this class. First of all, 2 to the third power is 8, 2 to the fifth power is 32, and 2 to the 10th is 1024. Kind of group these by color by different bases. So 3 to the third power gives you 27. 8 to the second power is 64, 9 to the second power is 81, and then 10 to the third power is 1000. Once again, I grouped all these by powers, or by bases, just so you can see what happens when you raise a different base to a power, just so we can make that distinction there. Let's go ahead and get started with looking at transformations of trigonometric functions. All right. So a basic overview here, as you can kind of see with this function here that I have at the top, I have y equals a times sine of b times x minus c plus d. Now that's a lot of letters. So let's decipher a little bit of what we know here. Okay. First of all, this a value right here that I'm going to highlight for you, this a value, that is going to be what tells us what our amplitude is. Okay, and it says right here that the absolute value of A is our amplitude. Okay, so A is always going to be a positive number. Okay, we always want to keep that in mind. That's always going to be the distance, basically half of whatever the height is right here. So this little distance, oops, let me try that with a pen, of course. So this little distance right here, from the top all the way down here, whatever bisects the graph, basically that's our amplitude. And it's the same, notice, for this graph here. Notice that it's the same above and below the x-axis. Okay? So our amplitude is always going to be that distance between the middle of our trig graph as well as the height of it, or the distance from the middle of it. Okay? The period, the next part is the period. Now all the period really is the distance between when the pattern starts for a trig graph. So for instance, right here, take a look at this right here. Notice how the period for this starts at 0, goes up, comes down, and then ends up right here. That repetitive pattern is what we consider the period. And all that is just the length of how far does it take to get from one revolution of the graph, basically. Okay, so the period is always going to be 2 pi divided by whatever this coefficient of b is. Okay, and we'll show you how to use that mathematically in a couple seconds here. The phase shift, okay, phase shift is always horizontal, okay, is this coefficient c. Now what we mean by phase shift is basically if we know the parent graph of our trigonometric function, which is either going to be sine or cosine, and we always know that sine starts at 0, 0, cosine starts at 1, 0, or 0, 1. Do we have a change from where we normally start? Okay, we can identify that by looking at whatever we're subtracting x by. And notice that it's minus c, so that means that it's always going to be the opposite sign of what's inside of those parentheses. Okay, so if it's negative 1, that means we shift it to the right 1 graph, or 1 distance, whatever that might be. Okay, and then last but not least, of course, is our vertical shift, which is d. The nice thing about this vertical shift is that it's not really dependent on anything in the function. It's just there. So how far up from the origin, or from 0 or 0, 1, if we're looking at the cosine graph, how far up or down does the graph go? Okay, same applies for the cosine function, and the only difference between the sine and cosine function compared to the tangent is that the period is pi over b. But for this lesson, we're going to look at just simply sine and cosine. For this part right here, go ahead and take a little bit of time, pause the video, and write down this part right here. Consider a function of the form y equals a times sine of b times x minus c plus d, or the same thing with cosine. Okay, so what I'm going to do is I'm actually going to give you an example here of one that we can use. Let's say we have, for instance, let's say we have y equals 3 times sine of 4 times x minus pi plus 2. Okay? So the amplitude here, remember, we take the absolute value of our coefficient. Okay? So let's say we have the coefficient A. We take the absolute value of 3. That means the amplitude has to be whatever the absolute value of 3 is, which is just going to be 3. Okay? The period, once again, we use this little formula, this 2 pi divided by b, and in this case, b is going to be this 4, so 2 pi over 4, which we can simplify to become pi over 2, or half a pi. Okay? So that means that every time we go to the right or to the left, pi over 2, that pattern of up, down repeats over and over again. So the next part, for part C, it kind of gets into generalities here. In general, the part that can cause a vertical stretch or shrink is always going to be our amplitude. In order for it to stretch, the amplitude has to be greater than 1. Okay, so for the stretch, A has to be greater than 1. For a shrink, I'm going to make sure this is absolute value here, the absolute value of A has to be less than 1. That causes a shrink. Okay, and then for a reflection, my A value has to be negative. Okay, so it has to be less than 0. Okay, and once again, we know that our amplitude is always going to be expressed as a positive number. Sometimes when we look at the coefficient of A, it's a negative number. All that implies is that we're reflecting over the x-axis, or over the x-axis. Okay, looking at the horizontal shift, what's my phase shift here? Well, that's going to be this C, and we always look at the opposite signs. The opposite value of a negative pi is going to be positive pi. So that means we're going to have a horizontal shift to the right, a distance of pi. Okay, and then what parameter causes the vertical shift? Well, that's the d value, the one that's independent of the function, and that's going to be a value that goes up 2. Okay, all right, so now let's go ahead and graph one of these functions here. So f of x equals sine times pi of x. Okay, so we want to take a look at what a, b, c, and d are. So looking at our amplitude, there's no coefficient here, so that means our amplitude is just going to be 1. Okay, there is a coefficient on my x here. So we're going to take our value, our little formula we had, so 2 pi over what my b value is, which is pi. So pi divided by pi cancels, and that means that our period is going to be 2. Okay, and there's nothing added inside the parentheses, so there's no phase shift, so C is going to be 0, and there's nothing being added, so it's just going to be 0 for our vertical shift as well. Okay, so now what we do when we graph it is we look at the normal sine function, no vertical or horizontal shift, so we always start at 0, 0 for sine. Okay, and then what we do after that is we adjust where our amplitude is. So that means we're going to have 1 here, -1 down here. And then because our period is 2, we're going to scale this graph so that way we have 1 here and then 2 here. Because we want to make sure that if our period is 2, we go through a whole cycle of the graph by the time we get to 2. So here's what that looks like. We top out right here, come down, and then there's our period right there. So that's what the graph of sine of pi of x looks like. Okay? Because notice once again, we have this motion where we go up, go through 0, 0, go down, and then come back up to the x-axis. Okay? So when we repeat that motion of going through the x-axis, going up, back down through the x-axis, and then back through the x-axis again, that shows that we have a period there. Okay? So this is a basic overview of how to graph or what our trigonometric functions looks like. In the next video, we're going to look at several examples of how to identify the different parts of a trig function.